All right, continuing on U substitution. Yes, it is a bit of a coincidence. Thank you, John. It's a shout out there to John. Okay, not that he uncovered a mistake, but it's a good question. Is it just a coincidence that you have the derivative here? Well, again, we are starting with some pretty simple examples. So we're going to move on where you're not going to see the derivative there. Okay, but what I'm saying is that when choosing U, okay, one must think very carefully. And if you see this, the derivative of U also, multiplied or divided or something like that in there. If you see that, that's a good thing, and that's actually going to make things easier. So this just represents a bit of an easier sort of question. But yes, it doesn't have to be there, but that is your clincher that this is U. All right, here you are. This is U. Okay. Now, as we did in the first example, du, right? And we can write du over dx to find the derivative, which we will one more time. What's the derivative of 3x minus 2? It is 3. And as we mentioned in the previous example, that this is not a ratio, but you can sort of treat it like one in a sense where you can actually multiply both sides kind of by this, in a sense, okay? And this actually could be written as 3 dx, or the derivative of 3x minus 2 is 3 times the derivative of x. Think of it like that, like the chain rule, right? It's like, is x our preferred variable? Are we differentiating with respect to time, or what are we doing? So, here we go. Du is 3 dx. So when we go over here, we've got u. Good. We've got du. That's awesome. So you might want to just, and I'm just going to rewrite this looking like this, okay? So 3x minus 2 to the power of 4. And then I'm going to write here times 3 dx. Okay? All right, so what we're going to be able to do is we're going to replace 3x minus 2 here with u, and we're also going to replace 3 dx with du. You see that? So du actually is going to go here. And it looks like this. So again, that substitution, right? U to the 4th. And then 3 dx is actually du. And that is, literally, that's 90% of this U substitution, is finding out what U is and rewriting this in terms of U only. So so the question is, where did this 3 go? Well, I just put the 3 over here, okay? This 3 did not come from here, really. I just rewrote the 3 to be beside the dx, so that you could see that 3 dx is actually equal to du. And that's why I replaced 3 dx in the next step with du. Okay? Does that help or no? Okay, so if this was a 2, let's say we had a 2 here. Okay? So let's just say, okay, I'm going to undo that again, but let's say this was 2 times this, and I move the 2 over here. See, this is 2 dx. It's not the same as 3 dx, so I could not replace, I couldn't just do that. Can't do that. That. 2 dx. Okay, now, in another example, in the next question, we're going to find out what to do if this happens. Yeah, I'll show you. I'll show you how to work that. Okay? Good questions. But let's follow through the example so I think you guys kind of can see, where we're going from here. So let's put that 3 back. All right. Yeah, and then of course here the antiderivatives, 1/5 u to the 4th, right? Plus c, and you put that back in there. Sorry, 5 there. 5 there. Thank you. 1 to the 5th. That's 3x minus 2 to the power 5 plus c. Okay. So in checking, and I didn't check my first example, but in checking this, again, what you want to do to check to see if you've integrated properly is really take the derivative of this, right, and see if you get this back, right? So let's try that. Let's take d dx or whatever of this, and so what we would do is we'd have 1/5, right? This 5 would come down. That's times I don't know why I keep wanting to put 4 there. Seriously. Okay, times 5. It's 5. 3x minus 2 to the power of 4 up there. Right? And times what? The derivative of the inside function times 3. So 5 times 1 over 5 is just 1. And we have 3x minus 2 to the power of 4. And that is the same as our original question there. See that? So if you take the derivative of the integral, or the derivative of the antiderivative, you should get the original function back, which is just the original function. Okay? We'll do another example. It is. It is the exact same. So
it doesn't matter if it's x,
no. Here's the answer to your question there. Yeah, when you take the antiderivative of this function, okay, this and this get dropped off when you take the antiderivative. Okay. Now that's only if this variable is the same as the variable that you're taking the antiderivative for. So yes, that's why this and this just kind of get dropped off when we take the antiderivative here, because this is du and this is in terms of u. Yeah, so if you have the same variable there, this part and this part are gone. They just kind of get dropped off. Yeah. Okay, so we ready for another example? Or should we stop and just summarize some things? Tell you what, let's write some notes out here. Okay, let's just stop and summarize. All right, so these are just some general notes here, just kind of, just talking notes, right? This is just sort of a discussion, just kind of a talking note. Nothing too formal, nothing too exaggerative, nothing too definite and technically sound either, I guess, because I've used a lot of quotes there. When I use quotes, sometimes it's like, this is not a hard and fast rule, this is more like kind of, just going by feel a little bit here. So when I say the inside function, right, we're looking for the function that sort of would look like the inner sort of layer, right, of that onion, right, that we can peel off. So the inner one. And also, we also said in this other example that if you can see something that would be an inner function and you can also see its derivative out there, boom, this is going to be an easy one, okay? I'd like to do an example for you now where you don't see that derivative out there. And there's just sort of kind of one more thing that we're going to have to do there. So let's see here now. Okay. Let's do this one. Okay, let's do this one right here. So let's say we're taking the integral of 3x minus 2 to the power of 4. Now, this looks very similar to the ones that we've done, but this is not the same. Why is it not the same? Because I don't have the 3 out there, do I? Okay, same as the last one, but with no 3. So let's say you're going to integrate this, and you say, well, it looks like I have an outside function, something to the 4th, and I have an inside function, 3x minus 2. So I'm going to say u is probably going to be this 3x minus 2. du is going to be 3 dx, okay? As we've established in the previous examples, the derivative of u is going to be the derivative of this. Write it as a differential. So in other words, it was du over dx, but just write the dx up here. So you look at this and you say, okay, that's the derivative of u, here's u, and I don't have 3 dx. Okay? Well, it's actually not that difficult to get the 3 in there. And you say, well, what do you mean, Mr. Maxwell? There's no 3 in there right now, so how can I just put a 3 in there? Well, we would have a 1 here, right? We would have a 1, okay? Now, what's another way to write 1? Oh, thank you. Someone ate a healthy breakfast this morning. Gets your brain working. We could write 3 as 3 over 3. Couldn't we also write 3 over 3 as 1/3 times 3? Yes, we can. So, let's just imagine for a moment, shall we, that I want this. I really want that, but I don't have a 3 there. I just have a 1. Well, If I want this, what else do I have to include to make that a reality? I have to include the 1/3 somewhere. So that's what you do. You put a 1/3 in there. And now you have that differential here, the partial differential 3dx in there, which is really, really good. But you say, Mr. Max, we got this 1/3 in here. What do you do with that? That makes this look quite a bit more complicated. Not really. The properties of integrals, very similar to the property of derivatives. You can take that 1/3 right out of there. That's just a constant. Who cares about it? So let's just do this right here. We'll leave that for later. And there you have your inner function with its derivative all in the same integral here. You see that? Brilliant, eh? Not great? So now this now turns out to be exactly like the question we just did. And instead of, where was it? Okay, so right here. So instead of having, that's it, right? Whoops, let's undo that. Wait, bring it back. Let's just copy that. Bring that back down. So if we just put that there, okay? Pretty close to this, except we gotta do something with that 1/3. And what happens at 1/3? Well, nothing. It just hangs out there. But it now could be multiplied by this other constant here. And so really the final answer is 1/15. Right? 3 times 5 times 3x minus 2 to the power of 5 plus c. And you say, well, I don't know if I believe you, Mr. Maxwell. Okay, fine. Might not be true. Huh? The 1/5 came from the 3 times 5. Right there. You see this 1/3 right here, brought down. This 1/5 came when we took the antiderivative of this. Say, add the 5, 1/5 there. Make sense? Yeah. I know this takes some time to process this. I get it. Okay? Taking all this information, you're putting it on the shelves of your brain. I get that. Not an easy process. Okay? Because you all have like really big, complex brains. And so you have to organize. You got to label the boxes. You got to say, hey, this is integral box here. Open it up. Make sure everything's organized inside that box. Now you got to throw this whole, thing into. I get it. Okay. That was just a little bit of a snicker break. Okay. Yes, John. If you want to back up to this step right here and say, hey, okay, du. I want to replace du, but I just have, dx. So what does dx equal? Yeah, technically you could, I guess, write this as 1/3 du equals dx. And then what you'd have to remember, though, when you replace, so that this 3 wouldn't be there, when you replace dx with du, right, which I actually didn't show that, I guess, here, sorry. Didn't show that step there. You're going to have to make sure that this 1/3 goes in there, too. So this would be the step right here. Let's put it in green. Right? So it would be like this. Integral of u to the 4th. And then without that 3 there, because we didn't have the 3, then it would be du. But then you have 1/3 du, so that 1/3 has to go somewhere. Then you can put it out here. Yeah, you could jump straight to there if you want. Okay? Really, you're doing the same thing, just at a different point in the process. So, yeah, if that makes more sense to you, then by all means, you can go ahead. You can solve for dx then. Just make sure whatever you do with du here goes into the integral. Okay, good thought, good question. Yeah, anybody else? Okay. All right. I think what I'm going to do is give you one to do on your own. Okay. Now I didn't prove this. I didn't check this, I guess. All right. But if you take the derivative of this, the 5 comes down, right? Which makes it 5/15, right? Which is 1/3. And then it's 3x minus 2 to the power of 4, and then it's times 3, right? So 1/3 and then times 3 would just be 1, so you get the original back there. Okay. Okay, so here's one to try on your own. Let's see if you can do this. Okay, cos of 4x dx. Find the integral there. Use U substitution. So think about what would be my inner function here. And go ahead and do it.